I have the pleasure to introduce the first talk. The first talk is about millimeter scale ultra-low power imaging system for intelligent edge monitoring. And it will be presented by Andrea Bajano Carbo. She's a PhD student at University of Michigan.
Good morning. So thank you for the introduction. My name is Andrea, and I'll be presenting my paper on millimeter scale ultra-low power imaging system for intelligent edge monitoring. Tiny IoT sensing systems have advantages over larger IoT devices since they are able to closely capture and analyze data right at the source. This allows them to be unobtrusive, which can be beneficial particularly for medical, animal, environmental, and industrial monitoring applications. Though they can provide advantages, tiny IoT systems pose the following key challenges. The first is designing a millimeter scale system, which involves integrating ICs in an extremely small footprint, which also makes developing and debugging these systems difficult. The other challenge with systems of this size is that a millimeter scale battery is used to maintain a small system dimension, which imposes a tight peak power and energy budget constraint. This constrained energy budget is hard to meet for imaging systems in particular, since they include computation and data-intensive digital signal processing and analytic algorithms to perform advanced tasks like object classification. Thirdly, the data footprint of imaging systems is higher than other sensing modalities, like temperature and pressure, while the amount of on-system memory is limited due to system size and power constraints. This memory constraint also limits the complexity of algorithms that can be used on the system. However, incorporating intelligence in IoT devices is essential in order to reduce the amount of raw image data that is offloaded. Most off-the-shelf solutions that provide a high data rate require a reference crystal and matching antenna and have a power consumption in the milliwatt range. Due to our size and power constraints, we use a crystal-less ultra-low power radio, which has a lower data rate, making it costly to offload large volumes of data. Finally, the neural network algorithms that are implemented on edge devices are often trained on high-quality image datasets, which do not take into account the non-idealities of an ultra-low power front end. In practice, this causes performance degradation. This paper proposes several solutions to these challenges. The first is addressed by stacking custom ultra-low power ICs vertically to increase the number of chips that can be integrated in a footprint compared to traditional 2D planar chip-to-chip connections. To deal with a constrained energy budget, we utilize behavior-specific power management modes to optimize the system's power consumption for the chosen application. A hierarchical event detection algorithm that exploits event sparsity is also used to reduce the frequency at which complex scene analysis is performed. Next, we use a combination of data compression techniques to reduce the memory footprint of images and neural network parameters. These methods not only reduce the intra- and inter-chip data movement energy, but also help to reduce the amount of wireless data egress. Finally, we add image correction layers to our neural network-based analysis to compensate for front-end non-idealities and maintain good performance. The system uses ultra-low power ICs from a family of custom chips that have been designed to be stacked and connected vertically. These ICs include a master controller, which contains a Cortex-M0 microprocessor, a power management unit, and a crystal-less radio that consumes less than 70 microwatts of average active power. The system uses a low-power image sensor layer that supports motion-triggered VGA image capture. The system also uses an image signal processing layer that performs on-the-fly JPEG compression and H.264 compression. Its neural engine has a peak efficiency of 1.5 TOPS per watt and enables deep neural network-based frame analysis. The system has 256 kilobytes of ultra-low leakage flash, an energy harvester layer, and a solar cell layer to enable sustained operation. The imaging system can be diced to a 10 by 10 millimeter form factor, which leaves exposed metal on the rims that we connect to help with development and debugging. The system can then be diced to its final size of 6 by 7 millimeters. One standalone operation has been verified on the larger system. These layers are connected in a daisy chain configuration and forward transactions using an open source ultra-low power bus protocol called MBus. The system uses a lithium battery, which is recharged using the solar cell and energy harvester layers. The power management unit generates 3 voltage domains from the single battery voltage and maintains a high conversion efficiency under loads ranging from nanowatts to hundreds of microwatts. The image sensor supports both a VGA image resolution as well as a subsampled 32 by 20 pixel resolution, which is used by the sensor to perform motion detection on chip. These frames are streamed directly to the image signal processor, which can perform compression and neural network-based analysis. The other processing element acts as the main layer and duty cycles unused layers. Figure A shows how unpackaged and thin chips are 3D stacked and interconnected. The front side of the PCB is used for stacking the ICs and is encapsulated in black epoxy to block out light because of light sensitivity of ultra-low power components. The image sensor is left exposed by attaching a lens barrel over it prior to encapsulation, which can be seen in Figure B. A second PCB provides spacing between passive components and the battery, so these can be placed above each other, and allows a solar cell to be encapsulated with clear epoxy so that it is exposed to light. The radio IC is connected to a metal trace loop antenna integrated within the PCB. The final standalone system measuring 6 by 7 millimeters is shown in Figure D. Though the millimeter scale imager system is programmable and can be used for various applications, it is demonstrated for a home surveillance scenario. The image sensor captures a highly subsampled frames at a rate of 1 frame per second, which is chosen to maintain low power but can be programmed to be higher, and performs motion detection on chip. When motion is detected, the image signal processor receives the subsampled frame and performs neural network-based person detection. If a person is not detected, the system returns to continuous motion detection mode. Otherwise, a VGA frame is taken by the image sensor and streamed to the signal processor to perform some image processing. This includes finding a region of interest by comparing a stored reference frame with the incoming frame. Image correction layers and face detection is performed on the VGA image. And only if a face is successfully detected will the system move on to perform face recognition. Finally, if a face is unrecognized, the region of interest will be compressed and either written to flash or sent wirelessly. The system's millimeter scale battery has a limited capacity, making power management crucial to achieve a standalone system with a reasonable operating lifetime. For this reason, we carefully optimize the system's power consumption for the chosen application. Most ICs in the proposed system are duty cycled according to the system's behavior, as shown in the figure. The image signal processor also allows for fine-grained software control of its SRAM banks, which can be put in low power retention mode without loss of data. The neural engine SRAM is partitioned into 7 variably sized blocks that can be selectively power gated to reduce leakage power consumption according to the algorithm storage requirements. The power management unit is adjusted at each mode to maximize the efficiency for the dynamic load, achieving an average efficiency of 64%. A hierarchical event detection algorithm is used to prune out irrelevant events that would otherwise wastefully consume energy without first determining their value to the user. Efficient motion detection using a highly subsampled frame is done in the front end, while other layers are set to sleep. Only once motion is detected will the system wake up the image signal processor, which will perform neural network-based person detection over this highly subsampled frame. Only once a person is detected will the image sensor take a full VGA frame, which consumes about 9 times more energy than the motion detection frame. This avoids taking a full frame every time an event that disturbs the scene occurs, such as a household pet. Face detection is then performed on the VGA frame, and only if both a face is detected and then recognized will the image be compressed and stored to flash or offloaded wirelessly. This figure shows that as the event probability decreases, hierarchical event detection enables significant power reduction. Further, the image signal processor computation power is always insignificant compared to the image sensor or the radio for the different cases where the event probabilities are varied, showing that the benefit of using this approach has small energy overheads. The proposed system has limited IC area for flash memory and on-chip SRAM, making it critical to use aggressive data compression techniques. We use a combination of 4 techniques. The first is JPEG compression, which is performed on the fly whenever a frame is streamed from the image sensor into the image signal processor. This reduces the memory footprint of storing images on chip and the SRAM leakage power by 11x, and allows a reference and current frame to be stored on chip, which reduces inter-chip data movement whenever analysis on these frames is being performed. We also leverage the image signal processor's customized H.264 compression engine to reduce the memory footprint of a VGA frame by 23x, which reduces both flash write energy and wireless egress energy. Change detection between a new frame and a reference frame stored on chip is also performed on the fly. Each 16 by 16 pixel block of a frame is encoded into a pattern vector and compared to the stored image to represent a non-rectangular region of interest. Because we use a customized H.264 compression algorithm that removes inter-pixel block dependence, we can compress only the non-rectangular region of interest while unchanged pixels are pruned. This allows us to achieve 135x compression, while change detection processing consumes less than 3 microjoules. Finally, we can decrease the wireless egress energy by only sending a map of the change detected blocks in the current frame, as well as the H.264 compressed region of interest to reconstruct the full image offline. We assume that the system is deployed in a stationary location so that the system and the user share the same reference image, which can be periodically reprogrammed. A scene is reconstructed by decompressing the unchanged pixel blocks from the reference image and combining it with the changed region of interest of the current frame. This can reduce the egress data by 130x. The compression gains achieved yield proportional energy savings when writing the image to flash and transmitting the data via the wireless transmitter. It also reduces the egress time to minutes and increases the VGA capacity from 0 up to 74, making the system more practical for deployment. Notably, the processing energy for these compression methods is negligible compared to the substantial energy savings. Our system uses a wide-angle, millimeter-scale lens for wide-view scene analysis and an ultra-low-power image sensor that lacks sophisticated image pre-processing. We found that these introduce both geometric and color distortion to the captured images, which negatively affect the performance of deep learning perceptual tasks trained on high-quality datasets. In fact, both of our performance metrics decreased by over 20% when we use data modeled after captured images. We propose image-correcting layers that can be executed on the image signal processor's neural engine using widely supported instructions, such as matrix multiplication and convolution, to compensate for artifacts and distortions. Because it does not require any extra hardware and has low memory and computational complexity, this method can be generalized to other constrained imaging systems that suffer from this degradation. The fisheye lens distortion is modeled by capturing checkerboard images using the system, and geometric distortion correction is achieved by using a flow field matrix that represents the learned vertical and horizontal pixel displacement vectors. Color correction is implicitly accomplished with a linear layer in our customized one-shot object detection network based off the popular YOLO algorithm, which we use for face detection. Training data images are modified using a color distortion matrix, which we obtain by capturing images of an edge spatial frequency response chart using the proposed system. In this way, the color correction matrix is implicitly learned. The results show significant improvement in both average intersection over union and average recall when image correction layers are applied, even after network pruning and quantization are done to allow for on-chip parameter storage. In fact, we demonstrate the benefit of using image correction layers for other constrained systems by using a smaller grayscale input image with reduced feature maps to demonstrate that our proposed solution still gives sensible performance for other cases. Our system achieves a total average power consumption of 49.6 microwatts and a lifetime of 7 days for our proposed intruder detection scenario. The combination of data and energy management methods, including H.264 compression, offline image reconstruction, hierarchical event detection, and optimized energy efficient modes, extends the lifetime by 13x. The total power consumption of the system when it is in sleep mode and the ISP, image signal processor, is not retaining any data is 7.35 microwatts, giving a total shelf life of 48 days without recharging. The figure on the right shows the full intruder detection scenario, including the energy consumption and execution time of each system behavior, which is sufficient for our target scenario where the event of interest is triggered infrequently. We use 2 different wireless radio transmission modes that trade off data rate and distance. To conclude, we have demonstrated a novel millimeter scale standalone system consuming about 50 microwatts that has embedded intelligence capabilities and can be used for tiny IoT monitoring applications. Our use of data and energy management techniques significantly extend the system's lifetime and are generalizable to other area and power-constrained systems. An example of this is our image correction layers, which improve neural network performance for ultra-low power devices. Having demonstrated a tiny IoT intelligent imaging system, analysis through a socio-technical and ethical lens is an essential next step, and we invite future work on these topics. Thank you.
So thank you. That was perfectly on time. Are there questions?
What is the power consumption when it works active? As of 50 microwatts, that's the average of standby and active.
So that's the average when we did an intruder detection scenario. So we assumed certain probabilities for each event. So for example, for the person detection, we assumed that it would only trigger motion every 20 minutes,
what's the power when it triggers? When it triggers and detects an image and analyzes it, what is the power consumption?
Sure, so I think that can be seen more clearly here. So each event, we computed the energy per event, so it really depends on, through your analysis, it depends on what event is taking place. So if you have motion occurring more frequently, or if you have a higher probability that person detection will then lead to higher neural network analysis taking place, then your average power will increase.
Thank you.
Thank you.
Thank you again for the presentation. On this slide, you say the average power consumption for 7 days. About how many intruder events would that be?
Thank you for that question. So as I mentioned, we base this off probabilities of motion happening, triggering every 20 minutes, and then I believe it was 1 in 5 events for person detection, face detection, and face recognition. So the total events, I don't know off the top of my head, but I'd be very happy to talk to you after and get that exact number.
Okay, thank you.
Thank you.
Hi, my question here.
Oh, sorry.
The question is, so do you have a similar question about the solar harvester and how much power it gets and all that?
Yep, so that was the harvesting capability that we calculated, which is about 10 microwatts for 10 kilolux light. Which again wouldn't be enough to sustain operation really for this kind of system because it has a higher average power consumption. We're really depending on the battery. So the real trade-off here is having a larger battery with a larger capacity or trying to keep the system area small. So while we do have solar cell and energy harvesting capabilities, I agree it really does depend on having a larger battery to be able to sustain this system for longer. But for our current application, our trade-off that we got was a 3.4 milliamp hour battery because that really was able to keep the dimension as small as possible, and that was what we really wanted to do for this system.
Thank you.
Thank you.
I have a question back here. How does this compare to other systems that try and serve the same kind of application, like other intruder detection systems that need to have a long lifetime? Has there been any other work that looks into this? And I have a kind of second unrelated question, which is the model you're running. Do you know what the total max or Gmax or sort of total compute load is for that model? Thanks.
Yeah, so to answer your first question, I think there aren't a lot of intruder detection, like for home surveillance, that are this small because there's not really a motivation to have a system that is so size and power constrained. But what we really wanted to do here was just show it as an example application. In my opinion, I think something like this, a tiny IoT device that is so small and is able to do all of this analysis, would be very interesting in industrial monitoring or environmental applications. So personally, I think using this for those kinds of applications would be much more interesting, and that would be something that I would like to see happen, because I think we get a lot more interesting data about animal behavior or hyperlocal environment data. I think that'd be very cool. Your second question, sorry, could you repeat it? I couldn't quite get that.
Sorry, yeah. I just want to get a sense of the total size of the model you're trying to run, like in Max or some other kind of measure of total compute.
Okay. So in Max, off the top of my head, again, for each of them, I could talk to you after. I'd be happy to give you those exact numbers. The neural networks that we were running were pretty small. So for the face detection, person detection, that was just 2 convolution layers and 2 fully connected layers. Again, a small customized network. We also we based it off a one-shot object detection for the face detection model. Slightly larger, but we customized it to fit our system. So that again was about 5 convolution layers. And then for face recognition, again, that was pretty small. It was about 5 convolution layers as well. So pretty constrained.
Thank you. Great paper.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving TinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SensiML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.